Okay, so let me just tell you one thing about this observation, that the shape operator for the sphere of radius r is just the identity map times 1 over r. This is, of course, like this because this is no surprise. This is no surprise since the Gauss map from what was this surface sigma to S2 is given by, what is the Gauss map? Gauss map'ini nasıl göstermiştik? U'la göstermiştik değil mi? From sigma. What is sigma? Sigma is the sphere of radius r actually. And what is the image of the Gauss map? It is the sphere with radius 1. And what is this map? At any point P, it sends this point to where the normal vector to the sphere at the point P. P is a point on this sphere, so the vector joining origin to P has length r. So if I just divide this vector by r, I will get the unit normal vector. Therefore, this map is just 1 over r times P. I may regard it this way, right? It takes, so we have two spheres, right? Like this. If you have a point here, P, the normal vector to this sphere at this point is nothing but, just join this to the origin, and then the point where this line intersects unit sphere is the image of this point, this map, Gauss map, UP. Değil mi? Bu noktadaki birim vektör nedir? Bu vektörün boyu bir hali, yani bu vektörü boyuna bölüyorum. Right? P divided by 1 over r. And shape operator was minus 1 times the derivative of u. U is basically the identity map, right? It takes a point P, it sends it P times a number, 2 times P, 3 times P. What is the derivative of identity map? It is just the identity map, right? F of x'in türevi nedir? Türevi 1 ama differential'ını alırsanız differential'ı identity. Değil mi? Çünkü türev map'i o noktada identity map veriyor. So, since this is basically the identity map, U star at P along a vector V is just derivative of this map, which is 1 over r times identity. So this is 1 over r times identity evaluated on this vector, which is just V. And shape operator was, by definition, minus the derivative, right, of U star of U. So it is minus 1 over r times V. Yani fonksiyon zaten küre için Gauss map'i identity map'inin bir katı, 3 katı, 5 katı. Türevi, identity'nin türevi gene identity. Değil mi? O yüzden türevi de kendisine eşit. Okay. Okay, second example. So this was our first example, sphere. Let gamma be a plane in R3. Then the unit
Hocam
normal.
kamerayı değiştirebilir misiniz acaba?
Tamam. Okay, our second example is the plane, a plane in R3. The unit normal vector field is a constant vector field, right? Namely, suppose this is your surface, okay, which is a plane. At any point, your normal vector is the same vector, right? It's a constant vector field. UP is, let's say, n0, okay? A constant vector field. What is the derivative of constant vector field? Hence, and actually, what is the Gauss map? Gauss map, U from the plane into S2. It sends every point to the same vector, which is n0, right? So it's a constant function. Constant function. Hence, the shape operator along any vector v at the point P will be what? Derivative of this or derivative of this map. It's the constant map, therefore this is just 0. So what was this? Minus V times UP minus, this is just n0 constant, derivative of a constant function is 0. Okay, so the shape operator for a plane is 0. Okay. So we have seen kind of two extreme cases. For the sphere, shape operator is identity map, basically, just a constant times identity. For a plane, shape operator is just 0, right? Let's see something in the middle. Let C be a cylinder, or the cylinder, given by the equation x squared y squared equals 1. What is this cylinder? It is just a circle in the plane, xy plane, and then you just take this circle and move along the z-axis, right? You get so-called a cylinder, right? Here is the z-axis. This is the x-axis, y-axis, and this is the z-axis. All right, this is the cylinder. So let's choose a point on the cylinder, any point P. Let's say P has coordinates X, Y, and Z. Then what is the unit normal vector? Of course, when I choose the normal vector, I have to make a choice, right? Because if your surface is orientable, then you can choose a normal vector field on the surface, but you have two choices. You choose one of them, and the other one is just minus that one. So in this case, which one should I will choose? I will choose the outer one. So it's just it is just XY0, right? Of course, I have to put this 0, where R is just X squared plus Y squared. Okay, so the normal vector at this point is what? Yani normal vector bu noktada şöyle değil mi? So it's like this. It has X, Y coordinates, no Z coordinate. It is unit because the length of this vector is just R. So this is my unit normal vector field. I can write this as what? This is just 1 over R times R is here constant. Actually, it is just 1. So this is just okay. X, Y, 0. So X, Y, 0. So this is just X times U1, Y times U2. U1, U2, U3 are the constant vector fields along the coordinate axis. Değil mi? Bu X yönündeki sabit vektör alanı, U2 Y yönündeki sabit vektör alanı, U3 de Z yönündeki sabit vektör alanı. Herhangi bir şey anlamazsanız bana hemen sorun. Hani beklemeyin. In geometry, you have to get used to the notation. Okay, notation is important. Compared to other, branches of mathematics, notation is very important. You have to get used to different kinds of derivatives and so on. And different kinds of derivatives are, distinguished by their notations. So it's a part of learning geometry that you get used to the notation. Okay. All right. So the tangent space at this point, C of the cylinder. So this is our cylinder, tangent space at this point. So it's something like this, right? Is this span of, I can write it also as like this, E1, E2, where E1 is again 1, 0, 0, which we also write this as U1, and E2 is 0, 1, 0. Okay. Now let's see. Oh, yeah. You're right. You're right. It should. Yeah. Sorry. Niye öyle yazdım? Okay, yeah. E1 is this, but E2 is not that one. E1 is not this either. E1 is just 0, 0, 1, and this is minus y x 0. So E1 is this vector. And E2 is the vector which goes around the circle minus y x. So it is this vector E2. Çemberin etrafında dönen vektör. Değil mi? X koordinatı negatif. No, it is not this one. It is the one pointing the other way. E2. Değil mi? If x and y coordinates of this point are positive, then the x coordinate of this vector E2 must be negative. Therefore, this vector should point in the negative x direction. So it goes into the blackboard. Okay. How can you check that these are so this is U1, this is not U1, this is U3. But let's just have this two. How can you check that whether these are really tangent vectors? Well, they should be perpendicular to the normal vector x, y, 0, and you can check that this is really the case, right? 0, 0, 1, dot product x, y, 0, it is 0, and E2 times U, so minus y x 0 dot product x y 0 x y 0, and what is this? This is minus xy plus xy, so it is 0. Okay. All right. Now let's see. Oh. Okay. Now let's compute the derivatives. Nabla E1 UP. So what is this? E1 is just U3, right? E1 is just U3. Right? E1 is the vector field U3. And then I have UP. UP is what? It is X over R times U1 plus Y over R times U2. Okay. I am taking R is constant here, right? 1 over R goes out, and then what is this? This is nothing but you take derivative of this function along U3. So this is just U3 of X times U1, and then U3 of Y, U2. But this is just derivative, directional derivative along the Z-axis. So this is just del X, del Z, and this is just del Y, del Z, which are both identically 0. So this is 0. And geometrically, this means what? This means the following. The normal vector field along this direction, E1. E1 is just going in the Z direction. The normal field along E1 doesn't change, of course, right? It doesn't change. The normal vector field is constant along the Z-axis. As you move parallel to the Z-axis, your normal vector doesn't change. Okay? So it is not a surprise. What about the other one? So E2 of UP well, this is just what? E2 is minus y x 0, this vector, and UP was x times U1 plus y times U2, right? Right. U is this. So this is 1 over R da vardı. I have also 1 over R. Yes. R. Vektör field'ımızda 1 bölü R var. Okay, yes. Now this is constant R, so it goes out 1 over R times, and then minus y x 0 of x U1 plus 1 over R times minus y x 0 y U2. What is this? I have to just take the derivative of the coefficient functions along this vector vectors and multiply the result by U1 and U2 respectively. And what will be the derivative? So that is equal to what? And nabla E2 of UP is just 1 over R times. So this vector minus y x 0 evaluated on this function plus 1 over R times, şöyle yazayım, 1 over R times minus y x 0 evaluated on the function y times U2. Bu vektörü buna yedirmek ne demek? Bu vektörle bunun gradient'ının product'ı olarak da yazabilirim. So this is just this vector dot product with the gradient of this function. What is the gradient of this function? Derivative of this with respect to x, derivative of this with respect to y, derivative of this with respect to z times U1 plus 1 over R times gradient of this function. Derivative with respect to x, derivative with respect to y, derivative with respect to z times u2. So from this, we will get what? Nabla E2 of UP is just, okay. From this, I will get minus R, no, sorry, minus Y. So 1 over R in 1 over R parenthesis, minus Y times U1 plus X times U2. Okay. Well, what was E2? E2 was minus YX. So this is 1 over R times X coordinate of this vector is minus Y, Y coordinate is X. So this is just 1 over R times this. It is just E2, I guess. Yes, okay. So derivative along E2 is just 1 over R times E2. It acts like scalar multiplication along this vector E2, right? It just changes its length. Okay. So aslında matris gibi de yazabilirdik. Yani matris gibi yazsak, değil mi? Neyse onu sonra yapayım. Okay. Let's look at this example, the saddle surface. M given by this equation. Z equals X times Y. Sometimes it's also written like this. The two are basically the same. There's only a coordinate change. If you let X, let's say U plus V and Y, U minus V, make a coordinate change, meaning that you rotate your XY plane 45 degrees, then it becomes U squared minus V squared. So basically these two surfaces are the same. One of them is obtained from the other one by just rotating the space in the XY plane 45 degrees. Okay?
Hocam acaba kamerayı çevirebilir misiniz?
Evet, çeviririm tabii ki. Kusura bakmayın. So the saddle surface M is given like this. The example we will consider is the surface given by Z equals XY. This is basically this surface Z equals X squared minus Y squared, and you see how we make the coordinate change, which transforms one surface to the other one. Therefore, this surface and this surface are just the same surface. One of them is obtained from the other one by rotating the space along the z-axis 45 degrees. Okay. So that's the linear algebra part. So, okay, let's come back. All right, so first I need to find, so this surface is something like this. Okay, something like this. I have to find a unit normal vector field. Okay, so normal vector field is, here's something like this. And we have to find an expression for this. For this, I consider the parameterization. Given by x here this x is not this x, okay? It is the parameterization x. It's a function. This x is a function from D2 into R3. And what is D2 in this case? D2 can be chosen to be R2, the whole plane. The UV plane is mapped to the surface, right? D is just the UV plane. Sorry, this is just R2 UV. And this is mapped into the surface. Okay. This is our map X. Evet, bunu belki big X gibi yapayım şöyle. Okay, now, well, if I have, of course, this parameterization, then I have my tangent vectors. Remember, I have at a point P, we have, let's say, x sub u and x sub v, tangent vectors. So what is x sub u? Derivative of this along v is just 1, 0, v. And what is x sub v? Derivative of this along the vector v, 0, 1, and u. Right? We just take derivatives of the coordinate functions. And what is the normal vector then? Vector can be chosen to be the cross product of these two tangent vectors. So it will be something like this. Right? UP. UP is just the cross product of these two vectors. Kayıt yapıyorum değil mi? Yeah, I have to divide by length. Hence, so UP can be taken as x sub u cross x sub v divided by the length of this vector, because it has to be a unit vector. So we have to take cross product of these two vectors. And what is that? So u1, u2, u3. X sub u is just 1, 0, v. X sub v, 0, 1, u. And I will divide it by its length. So U sub V is just, when you take the cross product, you will get what? 0, buradan eksi V. Şuradan da eksi U gelecek. Buradan da 1 gelecek. So this is the cross product. I divide this by the length of this vector. So it is just minus V minus U1 divided by 1 plus U squared plus V squared. Okay. Okay, so okay, all right. So we need to, so SPV is just following. Okay, V demeyeyim de şöyle. SP A times U1 plus V times U2 şimdi bir tane nokta da yapacağım. P'yi şu nokta seçersek 0, 0, 0 seçelim. Then UP is just 0, 0, 1. So we are at this point. Origin, and U is the vector, just the vector, unit vector along the z-axis. And what are the tangent vectors? Then x sub U. So x sub U is just, it was 1, 0, V. U and V are the same. So x sub U is just 1, 0, 0, which is just U1. And x sub, so x sub U is 1, 0, 0, which is U1. And x sub V is 0, 1, 0, which is U2. Okay, so x sub U is just 1, 0, 0, which is U1, and x sub V 0, 1, 0, which is U2. And if you compute this, okay, so along any vector, so TPM surface is just, of course, this is the span of U1 and U2. In this case, here P is just the point 0, 0, 0, okay? It is the single point. And this map is given by this expression. So B times U1 plus A times U2. So this coefficient switches. Now let's see why this is the case. So SPU1, what is this? This is just the derivative along U1 of what? Of U, right? The tangent vector field. Tangent vector field is just this gadget. So here minus nabla times U1
Hocam kameraya yine bir şeyler oldu da düzeltebilir misiniz acaba?
dondu mu?
Yakınlaştı yine kendi kendine, bir de yanlış tarafta sanırım.
Tamam, özür dilerim. Okay, now we would like to compute this gadget. Except U is just at the point 0, 0, 0. It is just the vector U1, and X sub V is just U2. So the tangent space has this gadget as basis U1 and U2. So U1 and U2 are vectors, let's say like this, okay? This is not the correct picture, but something like this. Okay, U1, U2. And we take shape operator at the point P, which is 0, 0, 0. It is just minus nabla U1, U. U is the vector field, unit normal vector field. Okay, now what is this? Şöyle yazayım. U1 boyunca bu vektör field'in türevini alacağız. Nedir bu? Minus V divided by this square root times U1 plus or minus U times this gadget U2 plus 1 over this gadget times U3, right? I take this vector field and take its covariant derivative along U1. Yani bu expression'ın U1 yönündeki directional türevini alacağım. U1'de nedir? Yani işte R3'teki şey tabii ki vektör alanımız. Bir dakika. Burada U1 okay, so here Burada dikkatli ol. Zaman geçti mi? 2 dakika var. Okay. Yeah, here we have to be careful. The thing is that our vector field given in the R3 space coordinates, right? But these vectors are in the space coordinates, so we have to be careful. Yeah. Well, let me do it next time. So the thing is that here, these are coordinates in the UV plane, but this is a vector in the 3 space. So I have to either write this vector in the UV plane or write this guys in the XYZ coordinates. Of course, this is not possible because these are functions only on the UV plane. So I have to write this vector in the UV plane. And I guess U1, so this will correspond to actually taking derivative along the U direction. So when you take derivative of this along U, you will get 0, but here you will get -1. And if you take derivative along U2, it will correspond to taking derivative along V. So it will be 1, 0, 0. That's why this two coefficients will switch, okay, U and V. But let's do it in more detail next time. All right, let's stop here.